Hello and welcome to a new video of English Smart Classes. This is going to be the fastest crash course ever on sheet metal operations. So without wasting any time, let's proceed to sheet metal operations. So what is actually sheet metal operations? When we are talking about sheet metal operations, we can usually have two types of sheet metal operations. Now sheet metal operations is basically a shearing operation, that is a shear cutting operation. It is a shear cutting operation which can be mainly divided into two categories. Those are punching and blanking operation. In punching operation, what will happen? Punching operation, it is the process of producing holes, and in this process we'll be producing disc. So what will happen? We'll be having a sheet metal from which we'll have to punch out a hole with the help of a punch. This is called as the punching operation. Here what will happen? Here the disc that will be produced, that is the disc which will be punched out from the sheet metal, will be the scrap material, and finally the sheet along with the hole that will be produced will be the final product. On the other hand, in case of blanking operation, what will happen? There will be a sheet metal, and from which we will punch out a disc. In case of blanking operation, the sheet metal along with the hole will be the scrap material, because it is not the desired product, but however the disc which will be produced will be the desired product. This will be the product. Now let us understand what is blanking actually, what is punching operation actually. So punching, okay, so punching is the process of producing holes. So let us draw for better understanding. Okay, let us consider this is the punch. Okay, so let's say we are having a sheet metal like this. This will be the die, and there will be some holders in order to hold the sheet metal. So what will happen here is that here the size of the die will be greater than that of the size of the punch. This will be clearance. This will be clearance. Okay, so what will happen here is that this is the punch, this is the sheet metal, this is the die which will be holding a die which will be there in order to punch out the hole, and this will be the holders. This will be the sheet metal holders. Now in case of punching operation, what will happen? In case of punching operation, the corrected size, that is the size of the hole, let me write first, corrected size is equal to the size of the punch, the size of the punch. That is, in case of punching operation, what will happen? The hole size will be equal to that of the punch size. That is, the hole that will be required, hole size is equal to the punch size. Now here we can see that the die size, that is the die diameter, will be greater than that of the hole diameter, that is the punch diameter, because hole diameter and punch diameter both will be equal. So what will happen in case of punching operation is that the die diameter dia. Let us consider it to be capital D. Dia will be equal to 2 times of clearance plus die allowance plus punch dia. Okay, this will be the formula. So we can write it as capital D is equal to 2C plus die allowance plus punch dia. Let us consider it to be small d. Okay, here we have considered 2C because we have considered the clearance to be a radial clearance. Radial clearance, that is, if this is the punch, we have considered the clearance to be present on both sides of the punch, and that is, we have considered in one side the C value of C, that is the value of clearance is of one side, that is the total clearance will be C plus C, that is twice C. In some questions there will be given that the clearance is diametral clearance, not radial clearance. If diametral clearance is given, diametral clearance, let's say C is given, then capital D will be equal to C plus die allowance plus diameter of the punch. Okay, now let's proceed to the next part, how to calculate this clearance. Now this clearance which is given, that is C, will be equal to 0.0032 d under root tau. Okay, here what is d? This is the formula for radial clearance. What is d? D is the thickness of the sheet material, thickness of sheet material. And what is tau? Tau is the shear stress of the sheet material, that is shear strength of the sheet material. Of the sheet material, let me write sheet material like this. Okay, if the clearance, that is the radial clearance, is not given in the question, and thickness and shear strength of the sheet material etc. are given, then we can find the radial clearance by using this formula. C is equal to 0.0032 d under root tau. In some questions, some other formulas might be given, such as C is equal to 0.0064 d under root tau, etc. This might be given in some questions. Then if it is given, then we would have to consider it, but otherwise the radial clearance will be C is equal to 0.0032 plus under root tau. Sorry, it is not plus. C is equal to 0.0032 d under root tau, where T is the thickness of the sheet material and tau is the shear strength of the sheet material. Okay, so now let's proceed to blanking. Let me add some slides first. Okay, blank slide, blank slide. Now what will happen in case of blanking operation? Wait a second. Now blanking operation. Blanking operation, it is the process of producing disk. Here what will happen? Here the corrected size will be equal to the diameter of the die, that is capital D. Okay, so what will happen is that we know that the die diameter will always be greater than that of the punch diameter, and some clearance will always be there, whether it is a radial clearance or a diametral clearance, we know that. Okay, So here, in case of blanking operation, the corrected size will be equal to the diameter of the die. That is, the hole size is equal to the diameter of die, that is equal to size of die. So what will be the punch diameter in case of blanking operation? In case of blanking operation, the punch diameter will be punch dia, small d. So what will be the punch dia? We know that the diameter of the die is equal to 2c plus diameter of the punch, 2c plus diameter of the punch. That is, let us ignore or neglect the diametral allowance for a second. So the diameter of the die is equal to 2c plus diameter of the punch. Therefore the diameter of the punch will be diameter of the die minus 2c. This will be the formula for diameter of the punch in case of blanking operation. Now let us find out the force required in blanking operation. Force, that is blanking force. Now let us first study about the punching force. Then we will proceed to the blanking force. Actually, blanking force and punching force both are same, because we will have to punch out a hole, or that is a punch out a circular part from the sheet material, whether it is a punching operation or a blanking operation. So both will be same. Let us call it as punching force. This is the maximum punching force. The maximum punching force will be how much? The maximum punching force F will be L T tau, LT tau, where L is what? Where L is the length of cut, T is the thickness of the sheet material, and tau is the shear strength of the sheet material. That is, L is the length of cut, T is the thickness of the sheet material, and tau is the shear strength. Sorry for interruption. Tau is the shear strength of the sheet material. Shear strength of the sheet material. Here F is the maximum punching force. F max is the maximum punching force, which will be equal to LT tau, and L is the length of cut, T is the thickness of the sheet material, and tau is the shear strength of the sheet material. Now what will be the length of cut? Length of cut, which will be denoted by L. Okay, so length of cut will be in case of a circular hole, actually the length of cut will be the periphery. So in case of a circular die, what will happen? In case of a circular die, if we need to punch out a circular hole out of a sheet material, or if we need to punch out if we need to produce a circular disc, in such case the length of cut will be equal to 2 pi r. 2 pi r, that is the perimeter, or in case of in terms of diameter, it will be pi d. Okay, this is when we need to punch out a circular hole. Now if we need to punch out a rectangular hole, what will happen here? In case of a rectangular hole, what will be the perimeter? Okay, so if it is A, let's say it is A, this is B, so the length of cut should be twice of A plus B. This will be the length of cut in case of a rectangular hole. That is, whenever we need to punch out a rectangular hole, this will be the formula. Now one of the most important topic will be the energy required for punching operation. this is the energy required for punching operation. Okay, so the energy required for punching operation can be generally written as E is equal to F max into PT, where PT is the penetration and P is the percentage of penetration. F max we already obtained. F max is equal to LT tau. Okay, so why will obtain this particular expression? Now let's see. Okay, so whenever there is a, let's say this is a punch, sorry for such poor drawing, let's say this is a punch. Okay, so what will happen is that there will be a sheet metal here like this, there will be a die, there will be a die. This will be the approach length x, this will be the thickness of the sheet material, which is T, this will be the die. Okay, so here we can draw a force versus displacement curve. So how will be the force versus displacement curve in case of punching operation? Okay, let's say in the left hand side there is force, which is the force required, and this is displacement. Now here, while traveling in the approach length, that is in the x length, that is the punch has been traveling, no force is exerted, so force is 0 till now. Then suddenly it comes in contact with that of the sheet metal, so the force suddenly increases. Then as it starts to penetrate, the force gradually decreases, and finally it becomes 0. So this will be the force required for punching operation. Okay, so if we convert it in rectangular terms, what will happen? If we convert it in rectangular terms, let's say if we convert it in rectangular terms, this is the maximum force, which is F max, this much is the penetration, let's say this is PT, this much is the penetration, and this area and this area both are equal. So what will happen? Actually this is force and this is displacement, so energy is equal to force into displacement. So here, from here we will obtain energy E is equal to F max into PT. Now we want our process to be economical, therefore we want to spend lesser amount of energy for a particular punching operation. So we need to, for this we need to reduce the maximum force that is required. This is to be reduced. So how can we reduce this? So we can reduce the force that is required for punching operation by shearing the punch. That is, by shearing the punch at a particular angle, we can reduce the force required for punching operation. Now without shearing, the force versus displacement curve can be seen to be a rectangle, but with shearing we will obtain a trapezoidal force versus displacement curve, which we will see right now. Wait a second, let me add few slides first. Okay, we are good to go. Now if we perform shearing of the punch, what will happen if we perform the shearing of punch? Let us consider this is the punch. Initially we have provided shear to that particular punch, this must shear, and this is the shear angle, which will be denoted by alpha, let's say, and this was the diameter. So what will be the shear angle? From here we can see that tan alpha is equal to P by B, that is, let me draw the triangle here for better understanding. This is D, this is alpha, this is S. So what will be the perpendicular? Perpendicular will be S and diameter will be D. Tan alpha is equal to S by D. Okay, so what will happen if we provide some some shear? The force that is been required for punching operation will reduce, and now the force versus displacement curve that we will be obtaining will be a trapezoidal curve. This will be force, this will be displacement, and the curve that will be obtained will be like this. This is T, this will be S minus T, and this will be T. This will be the new force, which will be less than earlier. This much will be X, which is the approach length. Okay, so what will happen here is that we can see that the total energy that is required. Okay, so let me correct one thing. Here the force that will be required for punching operation will reduce, but however the energy required will remain the same. Energy required will be same. The energy required will be E is equal to, wait a second, E is equal to Fs. Therefore, now what will happen here is that after providing a shear to the tool, the force that is been required for punching out the hole will reduce, and the new force that will obtain is F is equal to F max into PT divided by S plus PT. This is the corrected formula. Okay, let me write this again. F is equal to F max into PT divided by S plus PT. This will be the corrected formula, which will give us the force required for punching operation. Okay, that's all for punching. Now one thing to remember is that sometimes what can happen is that if the length of the sheet metal is more than that of the length of cutter, then in such case the length of cut will be the length of cutter. Now if the length of sheet metal is less than that of the length of cutter, then what can happen is that then the length of cut will be equal to the length of sheet metal. Okay, this we will better understand this while solving the numericals. In the next video we will be solving the numericals of past 15 years questions from this particular topic. So with this, let's wrap this video. Thank you.